Yeah, thank you for the introduction. My name is Robert. Today I'll be talking about learning to predict arbitrary quantum processes. This is a joint work with Sitan, Chen, and John Preskill. So recently we've seen a lot of progress in understanding how to efficiently learn and make predictions about quantum states, such as the progress in classical shadow and shadow tomography, or in learning Hamiltonians from gift state, etc. However, there's much less understanding in how to efficiently learn models to predict quantum circuits, or more generally, quantum processes. And in today's talk, I would like to talk about some of our recent progress in understanding this question. In particular, in this work, we're going to focus on training a machine learning model to predict functions of the following form. So the functions would take in a quantum state, an n-qubit quantum state rho, as well as an n-qubit observable b. And the output of the function would be a real value corresponding to evolving this input quantum state rho under some unknown quantum process, or just CP/TB map, and then measuring the output state property b. So in this function, this essentially includes any function that can be computed by a quantum computer. And more generally, if you don't place any restriction on the CP/TB map, then such a function also requires, say, an exponential amount of time to compute on quantum computer. So these kind of problems arises in many different examples. For example, people have been thinking about training machine learning models to predict outcomes of physical experiments, say in chemical experiments or other type of material science experiments. In those kind of cases, you can think of this unknown CP/TB map as the physical or the chemical process that's happening in the lab. The second example arises in quantum machine learning, where people try to train quantum neural network. This is actually the same question as this, where we're focusing on CP/TB map E that's given by some ansatz for a parameterized quantum circuit. And the final example, another example, is in speeding up complex quantum dynamics. So people have been wondering the possibility about training a machine learning model such that it can learn some 16th approximate representation for some complex quantum dynamics. So when we try to predict outcomes of this quantum dynamics, we don't have to simulate the entire process, which might require many, many quantum gates. But perhaps using the machine learning model, it can just predict the outcomes much more efficiently. So more precisely, in today's talk, the goal is to perform the following. That is, we're given some n-qubit CP/TB map E that represents a very high complexity quantum process. And we assume that we have the ability to perform some experiments on this unknown CP/TB map to create a data set. And we would like to use that data set to learn a low complexity model, so that given properties of the input state, we can use this learned low complexity model to predict properties of the output state. So that's essentially the goal. And in this talk, I would like to separate this into three parts. First, I would talk about a classical version of this problem. Then I would talk about a restrictive version. And finally, utilizing the idea in the restrictive version to generalize it back to the original problem that I just mentioned. So we're going to begin with the first on the classical version of this problem. Now, this problem has actually been studied for a very long time. And it's well known that it's quite a challenging one. So in this classical problem, we are given some high complexity classical Boolean circuit. And the input is essentially an n-bit string x. And the output is basically the first bit after we run the classical circuit on the input x. So in the quantum way, we can also write it out as trace of z1 apply onto the output state c of xx. So in general, if we don't assume anything about the Boolean circuit, then this function fc can be thought of as an exponentially long vector without any structure. So each entry of this vector corresponds to essentially the output of this function given some input x. And since there is no structure, learning such a function is very, very challenging. So for example, we can look at the worst case. So if you wanted to learn a model such that for all input, we can predict this fc of x up to some constant error, then one can easily show that we must query all the input. And hence the query complexity as well as sample complexity and computational complexity would all grow exponentially in n. And the reason is pretty straightforward. It's just because if you didn't query a particular input, you don't know what the corresponding output is. So you cannot guarantee a worst case prediction error. And because there's no structure, it's even harder in the average case. So you just wanted to learn a model so that on average, when we sampled an input x from uniformly from the hypercube, such that the average prediction error is upper bounded by a constant, say 0.5, one could also similarly prove that the query complexity grows exponentially in system size. And the idea is also pretty straightforward, is that if you only query, say, half of the inputs, then now for the other half, you have no idea what they are. So your prediction error would be lower bounded by 0.5. So now we can see that for this classical problem, both the worst case and the average case are very hard. It's exponentially hard. And now what we would like to do is to look at a corresponding version of this in a quantum setting. So in the classical problem, another way to think about it is where the inputs are essentially just these bit strings, which are like poles on the block spheres. And we know that this is exponentially hard. And now let's look at a corresponding problem where instead of having a classical Boolean circuit, we replace it by some high complexity quantum process. And instead of having bit string as the input, we replace it by saying having some product state as input. But the output is the same. We just wanted to estimate the expectation value of Z1 on the output state. And throughout this talk, I'm going to work with this observable O, which is a highly complex observable. It's essentially the Heisenberg evolution of Z1 under this unknown quantum process E. So predicting the output state property after evolving under this quantum process is exactly the same as predicting the expectation value of this observable O applied onto the input product state. And the question we would like to understand is this problem harder than the original classical problem? And for this, we're going to focus on the following data set. That is, we're going to perform experiments by just sampling random product state, feeding it into this quantum process, and measuring the first qubit. We're going to do that for some rounds. And after doing this, we are going to generate this classical data set about this output state property O, which is essentially a bunch of pairs of product state mapping to a real value YL, where the expectation value of YL is equal to the output state property for this input state psi L. And now, having this classical data set, we would like to understand, given a new product state psi, can we predict the output state property of psi accurately? So one can think a little bit about how this connects back to the classical problem. In the classical problem, this observable O would just be a diagonal matrix where the diagonal is an exponentially long vector, and the input is just this classical bit string. So now if we look at the worst case situation, if you wanted to be able to learn a model so that for all product state we can predict it accurately, then it's not hard to show that this problem is at least as hard as the classical problem. And hence, the query complexity would have to be also scaling exponentially in system size n. And now we can also look at the average case. So in the average case, say we wanted to learn a model so that when we randomly draw a product state, so for example, for each qubit, we just sample uniformly from the block sphere to generate this n-qubit product state. We would like to see if the average prediction error can be made, say, smaller than 0.5 efficiently. So in the classical case, we know that this is still exponentially hard. And we would like to see if it's still exponentially hard in the quantum case. And one of the key findings in this work is that, surprisingly, the answer is no. We can actually solve this problem in quasi-polynomial time. And the key idea behind this, and the separation between classical and quantum, come from the existence of a low-weight approximation. So if you write out this output state property O in terms of the Pauli basis, and now after doing that, we just throw away all the Pauli operator that acts on more than, say, k qubits. So we set k to be some value, and then if it acts too many qubits, we just throw it away. This creates this low-weight observable O low. In the paper, we proved the following lemma, showing that O low actually approximates O well. More precisely, it's this inequality, and the interpretation is that for most product state psi, the expectation value of O on psi is approximately the same as the expectation value of this low-weight observable O low on psi. In particular, the deviation between the two will decay exponentially as we scale up k. So by choosing k to be some small constant, it will already be a very small difference. Small value. It would be a small distance. And such a lower approximation doesn't hold in the classical case. That is when we take expectation value not with respect to random product state, but just with respect to random bit strings. In the classical case, one could also do this. And what one would find is that even if you choose k to be a very large value, the difference between them can still be as large as a constant, so it doesn't decay. And the intuition behind this is that in the classical case, all of these inputs are perfectly distinguishable. So if you know about one of them, that actually doesn't tell you anything about the other. And that's why there's this exponential scaling. However, when you have quantum state inputs, it's no longer the case. So they're not perfectly distinguishable, meaning that they have some kind of overlap. So knowing one actually tells you a lot of information about nearby quantum states. And that kind of overlap between quantum states is essentially captured by these low-weight approximation observable, this OLO. And hence, using this OLO, one can just predict a bunch of different quantum state inputs. So now using this lower approximation, we can have this very basic idea for designing this ML model. That is, we just try to learn this low-weight observable, which has a much lower complexity than the full observable O. So we pick some small value k, and then try to learn it. So learning this can be done by just learning all these Pauli coefficient alpha p. And we can learn them by utilizing this Fourier transform lemma, telling us how one can utilize this classical data set to get an estimate for alpha p. However, even though it's equal in expectation value, if you take a finite set n, there's going to be statistical fluctuation. And the larger capital N is, the smaller the fluctuation would be, and the closer we can learn this low-weight observable. So now this raises a very important question, that is, how large should this data size capital N in the data set be so that the learned observable is close to the true low-weight observable? And in this work, another interesting finding is that we found that this capital N can be set to be only logarithmically in the system size. So you have 100 qubit, now you just need like log 100, order log 100. In order to show this, in the paper we actually have to look at a very, very different task, which is on optimizing quantum Hamiltonians. So in this task, we are given some n-qubit k-local Hamiltonian H, and we would like to find a state that tries to optimize the energy. Particularly, we want to have an algorithm that have a guarantee on the energy based on the description of this Hamiltonian H. And more precisely, based on all these Pauli coefficients alpha p. And the work, we given an optimization algorithm that improves upon what we previously know, which can essentially find a product state approximation that approximately optimizes the energy. So what we're going to do then is utilizing the rigorous guarantee coming from this improved algorithm to prove some inequality, which is quite related to this quantum KKL inequality that was mentioned in the previous talk. So in this work, we prove a quantum version of a very famous inequality known as the Bonham-Blus inequality, which appears in classical harmonic analysis decades ago. And the quantum version essentially states the following. Suppose you are given an observable O that only consists of Pauli terms that acts on at most k qubit. So you can see that it's essentially this low-weight observable that we've been looking at. Then when we treat the Pauli coefficient alpha as a long vector, this alpha vector, there's this norm, the 2k over k plus 1 norm of this vector would be upper bounded by the right-hand side. And how to think about this norm, essentially, if you plug in k equal to 1, then this is just a 1 norm. And if you plug in, say, k that's a small value, then it would start to go closer and closer to 2. But it would always be less than 2. So it's essentially a norm between 1 and 2. And that's quite important, that it's actually less than 2. So now the right-hand side, since we're going to pick k to be some small value, 2 to the order of k log k is not going to be too large. And this is essentially just bounded by the spectral norm of O, which usually is also upper bounded by some constant. So now what this inequality tells us is the second insight. So we have a first insight about learning low-weight observable, and the second insight essentially tells us that these Pauli coefficient in this low-weight observable is approximately sparse because of this inequality. And the intuition of this is, for people that are familiar with compressed sensing, like in compressed sensing, we have typically, if there's some unknown vector that's very high dimensional, and we have, say, a 1 norm bound to it, then basically that means it's approximately sparse, and we can learn that vector very efficiently. And that's also what's happening here. because we have some vector norm bound that's somewhere between 1 norm and 2 norm. So now the ML algorithm essentially does the following. It's a very simple algorithm and only has like 4 lines. We just go through all the Pauli terms that don't act on too many qubits, say upper bounded by k. We use the Fourier transform lemma to get an estimate for the Pauli coefficient alpha p. And now if we see that the alpha p value is quite close to 0, we just set it to 0. And then the final learned observable is just given by the sum of alpha hat p times p. So the intuition behind this algorithm is that since this O low is approximately sparse, we can just set many of its value to be 0 without changing it too much. And furthermore, by doing this setting to 0, we essentially kill a lot of the statistical fluctuation. So this alpha vector is generally quite long, and since n is finite, there's going to be fluctuation over all of them. And together, that could cause the difference between the learned observable and the true one to be very different. But now, since we're just setting a bunch of them to be that are close to 0 to be 0, we essentially kill this fluctuation. And hence, we can establish the following rigorous guarantee for learning this highly complex observable O, which corresponds to the output state property. That is, for any epsilon and epsilon prime, given a training set size that scales logarithmically in system size and quasi-polynomially in 1 over epsilon and 1 over epsilon prime, we can show that the prediction error, the average prediction error, average over these random product state, is essentially upper bounded by that of epsilon and epsilon prime. So note that this prediction error is the prediction error for using this learned observable to predict this highly complex observable O. So now what we have seen is that for the classical problem, this is exponentially hard, but somehow, quite surprisingly, in the quantum problem, it becomes quasi-polynomially easy. And now, let's use all these ideas to generalize back to the original quantum problem. So in the restricted case, we're focusing on product state input and Z1 as output. And the original one that we set out to do is to consider input state that can be highly entangled, and we wanted to predict more observable B. So here we're going to focus on B, that's a sum of few body terms. And we're going to use this data set, which essentially considers random product state inputs and then perform randomized product measurement at the end. So it's just slightly different from the previous one. And now, given this classical data set and a particular input state and a particular observable that we would like to predict, the algorithm essentially works as follows. First, we use the observable and this data set plus classical shadow formalism to create this new data set for this output state property associated to this observable B. That is, it's a pair of product state mapping to real value where the expectation value of real value corresponds to the output state property for this input psi L. And now the algorithm is essentially the same as before. You just go through all the low way Pauli, estimate it, truncate things that are too small. And now the final learned observable O hat low is just given by this form, which only consists of few body terms. And finally, one just take in the input state and apply this O hat low on top of it, and that's our prediction. So doing that is actually very simple because as we see, O hat low only consists of few body Pauli. So by knowing the reduced density matrix of this input state rho, we can already estimate this trace. And then using the same set of techniques, one can prove that this would be quite close to this trace of B, E of rho, which is a function that we wanted to predict. So there are several surprising aspects of this ML algorithm. First is essentially, one can show that using this algorithm, we can learn to predict a very deep circuit, exponentially deep circuit, up to a constant relative average error from only a very small amount of samples. And furthermore, this algorithm is computationally efficient. And after learning from only product state inputs, this algorithm can predict well on entangled states. So now to conclude, in this work, we give computationally efficient learning algorithms that can learn to predict the output of a quantum process with arbitrarily high complexity. And this result essentially highlights the potential that maybe in the future, a machine learning model can predict outcomes of a complex quantum dynamics much faster than running the process itself. And that's it for my talk. Thank you so much for listening.
Sure, that's fine. So this might be a naive question, but O low, can we assume that that's near equilibration for the observable?
Yeah, that's when you say equilibration, I would imagine that you're saying something like, what do you mean equilibration in terms of?
If we were considering like a dynamical setup where O could, where O, there would be some point where O equals O would be equilibrated with the system. So for this system, like O low, we kind of would need to be equilibrated in order to have that approximate, in order to be approximately equal to that's the value of the observable, right?
Oh, actually, yeah, but that's a good question. So this really holds for any quantum process. So this evolution can even be quite short time. So you haven't equilibrated yet, and this lemma would still hold. So basically, even if the observable O has not been equilibrated, we can still do this lower approximation. Yeah.
So it seems to be kind of very strange and intuitive that in the guarantee for learning O, you actually throw away a lot of information, right? You set a bunch of alphas that are small to 0. Can you comment on whether you might be able to do better by some other scheme potentially, or?
Yeah, so I guess the question was, this seems like quite a strange algorithm, and is it possible to do even better than this algorithm? I hope that's.
Yeah, without setting alpha.
Oh, yeah, okay. So we can also consider a case where we don't do that step, and now the sample complexity will become much larger. It will be a large polynomial in n instead of this log n type scaling. So I think in at least from analysis, it seems to be very important that you do this additional step of setting things to be 0. Otherwise, there's going to be too many fluctuation because there's just too many different alpha. And the learned observable would just become very different from the true one if you don't take the number of data point to be a large polynomial in system size. But here, by doing that additional step, you can turn this large polynomial in system size to just log n.
I guess thank you. Wonder if it's possible to adaptively use the training data.
Yeah, that's also a good question. So more precisely, I think the question is asking, is it possible to not just use a fixed set of data, for example, like here, we just perform some randomized experiments and get a data in order to learn more efficiently. So to be honest, I'm not sure about this problem. It could be possible, but something like what Sitan also just talked about a few talks earlier, like for example, if we wanted to learn quantum states, we wanted to do quantum state tomography, doing things adaptively actually doesn't really help too much. Like maybe just by a constant factor, but not generally if the goal is to get small trace distance. However, this is a very different task. So it is possible that doing things adaptively could help, but at the moment I don't really know how I would do that. I have some idea, but I don't know how to prove that it's actually better than the one we did it here.
You define your quantum path, and if I replace all the operator by diagonal operator, you can define some corresponding classical functions there. This is a bit different from the classical path that you were comparing, but is there a proof method of this path applicable to this diagonalized differential testing if I define this way?
So actually, like, okay, so all of these results holds for any observable O. So if it's diagonal, it would still apply. And actually, it does just go back to almost exactly the same as the classical problem, because it's not quite. Like in this case, the classical problem is essentially any diagonal matrix where there is an equal number of 1 and -1 in the observable.
On average part.
Yes.
If I apply this, your method to diagonalize the classical thing, it's still easy. So
Yeah. So Yeah, the difference comes from where the average case is defined. So in the classical problem, the average is over all the bit strings, but here we're averaging over product states. Yes, yes. So there is that difference, and that actually causes this to become easier. And this is related to this fact about in the classical case, if it's input just perfectly distinguishable, then that's much harder. But if it's quantum state, it actually becomes easier.
Okay, thank you.
Okay.